Hello students, I am Tanmay and welcome you all in my channel Chemistry and History of Molecules. So today we will discuss about an important topic, that is aromatic electrophilic substitution on biphenyls. Previously I have uploaded some videos about basic concept about aromatic electrophilic substitution, reactivity difference between simple double bond versus benzene and aromatic nucleophilic substitution. Those I suggest you please go through those videos because those are the basic backbone for this topic like this applying. Okay, so I suggest you please see those videos and after that you come to watch this video. This will be helpful. And what we are going to discuss today, we will discuss about the aromatic electrophilic substitution on biphenyl. Interesting part of this molecule is that two benzene rings are connected to each other with a conjugation, means it is sp2, it is sp2, so this. So today's lecture will cover few points like the basic concept, reaction mechanism, effect of substituent like nitro, methyl, hydroxyl, phenolic type, etc. So we are going to learn today. So lots of chemistry we learn today. So let's start. So as you can see, this biphenyl, this looks like this. This is, and we know like benzene, every carbon has p orbital with one electron, means this. So this makes the system special. Why? Because it has a pi electron, and there are other orbital also, so they are in conjugation. Fine. So if you do anything on a particular nucleus, that will affect the other nucleus. So conclusion, so one nucleus, so the electronic property of one nucleus will affect the other. It is electronic, I should write. Electronic properties. So what is that? So keep this statement in your mind. Okay, so the electronic property of one nucleus will affect the other one. So this is the main basic idea needed to understand this topic. Now let's go to the inside. So before going to details, I will give you a very fast idea about this. So let's consider one part, this as a Z. Okay, so this is our product is, so now its system will look like this. Why I am doing this? To make the situation little simple. So this thing I have described in the previous video very way about the basic concept of mechanism of electrophilic aromatic substitution. So just I am giving a very fast understanding about this. So what is possible? So what is para? So if it is para attack, so this is a para attack. So what can happen? So this is the Z. Z means this biphenyl. So para means this is hydrogen, this is E. So plus charge is here. So it has a canonical form, that is it can come here and it may result. This is so double bond is here right now, plus charge is here. Another canonical form possible, that is Z. This will come here, this and plus charge is here, EH. Okay, fine. If it is meta attack, if para attack, now let's consider about the meta attack. E plus meta attack. So what will happen? So this is meta means this is E, this is H. So chances is the plus charge may come here. So canonical form it will come. So this plus charge is here right now. This is E. This is, I am going very fast, I know, because I have already described. So if you feel any difficulty, please go through the previous one where I have explained this very slowly. Okay, so it will come here. This is E and H. So this is the meta, and what is the ortho? The ortho is E plus ortho substitution this is Z, this is H, this is E, so plus charge is here. So both possible. I am just showing one. You will have the plus charge here in the one canonical form. Okay. So this, so it will come here. So plus charge will come here. This another canonical form. Now it will come here. So Z. This is the double bond. This is here. Plus charge is here. So H and E. Now see, previously if I have taken this arrow from this side, means sorry. Okay, I believe this is because little confusion. So let's change. I have drawn this, but you may feel little confused. Why? This. Okay, so now it is, I guess, clear. Did I make this same mistake? No, this is fine and this is fine, no problem. So what we have learned, this is actually para substitution. This is meta substitution. This is ortho substitution. Now the basic idea we will find from here. I suggest you please look at carefully. Now what is the basic thing we are going to learn from here? See, we will focus the canonical form where charge is on Z. In case of para, Z is directly attached to the positive charge. Now in case of this is meta, there is no positive charge attached to the Z. Okay, so no. But in case of ortho, see this canonical form, this is attached to Z. Now this is our main concern. We will focus. So let's clean the letter. Okay, before cleaning I will give you here. Now focus on this. So now write the Z thing. Z means a phenyl. This, and attached to it this electrophile and hydrogen. Okay, so position is here. And keep it in mind, this is the Mesenheimer complex, which energetically resembles to the reactant. Okay, this is this is a sigma complex. So this is energetically closer to the reactant. So which path the corresponding energy of activation is lesser, that part will be followed. Okay, so that I wonder why the corresponding energy of activation of this pathway means para substitution and ortho substitution less. I will explain now. Now this. So as you can see here, this is positive charge. Now this positive charge is stabilized by the resonance of the another ring. So this is phenyl, plus charge is here, this, and try to understand this. This is a very important and basic of this concept. Otherwise it is very difficult to understand this biphenyl system. E and H, and this is the plus charge. This. Fine. So in this, I made mistake. This. Fine. Now see, there are other three canonical forms. Charge will be one here. Okay. So other canonical forms means stabilization. Same thing is possible in case of this also. So let me clean the meta substitution. Now how? See, let's draw this thing properly. So this is the phenyl. Now this is hydrogen. This is electrophilic, E plus, and this is plus charge is now here. So this versus this. Now you can think that it can be donated with the canonical form. This is EH. So double bond. So previous was this. Now plus charge is at this side. Okay. So other canonical form also possible. So here other canonical forms. Okay, so 1, 2 total there will be 3. Fine. Now the question is, what we got from this, that this and this both is capable to provide stabilization for the corresponding sigma complex. Okay, so if it is, then as I told, if there are, according to microscopic reversibility, principle of microscopic reversibility, if there are infinite number of options for the particular reactant to go to a product, the corresponding path will be followed for a reaction which is associated with the lowest energy of activation. Now question, meta, there is no such stabilization, so corresponding energy of activation is less. In case of ortho and para, there is some stabilization. Now question is, which one is more? And if the extent of stabilization is more, then the probability or reaction will follow that path. Okay, so no problem. So this versus this, and I suggest you, please keep it in mind, many times people come to have a right explanation via a wrong way. So try to keep this explanation properly in your mind. It's fine. Now see, this is a para, this is ortho. If you look at, let me draw it again. This so phenyl, this is electrophile, this is hydrogen, fine, and let's consider the plus charge is at this center, fine, and similarly you have hydrogen at this position, fine. So now think, previously there was not that much repulsion because these were hydrogens, small element, but right now see there is a electrophile attached, so there is a chance of repulsion. So that's a negative point. Okay, I am not telling that it is very unstable. I am not saying. I am comparing this versus this. So we have to consider about the stabilization and unstabilization factors, and at the end we will conclude which one is more stable. Fine. So this is, but this is not here. So from that point of view, this is more stable. Second, this is, you can see, ortho-benzoquinone derivative. This is a para. Because positive charge at this position will be stabilized. So positive charge needs to come here. So if it wants to come here, there is an ortho-benzoquinone which is little less stable compared to the para one because of conjugation. Fine. So from this study we understood that this is relatively more stable, less stable compared to this. That is the reason why the aromatic electrophilic substitution on biphenyls, generally, I suggest generally, I write here, generally para position. Now why I told generally? Because I did not mention what is the nature of electrophile. So how can I say there is some differences or ideas which you can understand after giving you some examples. Okay. So now you can see two examples. This will clear the whatever you have learned, proof of this concept. So if you take nitric acid, sulfuric acid, this is also called mixed acid. And here the electrophile is NO2 plus. This is the electrophile. Okay. And one thing I forgot to say, I just saw the sigma complex, but sigma complex will eliminate the proton and finally end up with the electrophilic substitution. Okay, so please keep it in mind. Fine. Nitronium ion. So nitronium ion, as I told, in case of biphenyl, it will prefer to take in the para position. See, the nitration is happened this. Okay, this is a para product. Now, similarly, instead of that, if you take acetic anhydride, what is the product? This is also a para substitution, para acetylation. Where this electrophile in this situation is CH3CO plus. Actually, this is the resonance form. Actual electrophile is CH3CO plus. Okay, it is the canonical form. So this is the electrophile and attack happens on the carbon center from this biphenyl nucleus. So this is the para-isomer. What is the advantage of this process? You can functionalize these into different products. For example, if you take this nitro and NaNO2 plus dilute HCl, then you will be end up with diazo, means this N2 plus for if you take dilute HCl, then it will be chloro. If you take sulfuric acid, then that is a bisulfate. So in this way, in this context, I want to mention that I have already made about a video about the basic concept and preparation of diazonium salt. Okay, you may go through for details understanding. Fine. This is nitro diazonium, and if you have diazonium, then that step, if you take this second step, you can take this Q plus cyanide and ultimately result with cyanation, then carboxylation. Or you may think that you have this, if you take this haloform reaction. Haloform reaction means sodium hydroxide, or you may say iodine. You can take a sodium hydroxide and ultimately result with this carboxylic acid derivative. So variety of this possible, and I have already made a video about haloform reaction, so please go through that. So this carboxylic acid. So this is the importance of this reaction. Now a very important question comes in front of us. Question is, we have discussed about the biphenyl, which is a symmetrical easy substrate. But what is the reactivity of a substituted biphenyl? Okay, so that is the difficulty. For example, if I must say what is the now if you do electrophilic substitution, aromatic electrophilic substitution on this nitro biphenyl, where the substitution will happen, and question why. Okay, so now we will discuss this topic in order to understand the more insight. Okay, let's continue the discussion, last part of this discussion. See, here this is a substituted biphenyl. So right now I should write aromatic electrophilic substitution on substituted biphenyls. Okay, fine. So now this. So one is nitro, having a very strong minus I or minus R both. This is a methyl. It's a weak effect, this is a plus I effect, and this is a OH or OMe having minus I, which is weak, mainly plus R effect. Minus I, but that is a very weak, so we will not consider this. Okay, fine. Now, so this, you can see this is a nitro derivative. So question first, let me write the product. This is mixed acid, as I told, nitronium ion, and ice water. What will be the product? Ice water is for work. I'll explain slowly. So this is the nitro thing, original we have, and the second nitration will happen at this carbon. Okay, why and how I'll explain. Now see, this is a mixed acid which will result this nitronium plus. Fine. So chances, there are two positions. This ring number 1 or ring number 2. Where it will go? This is actually an electron deficient. Try to understand, very easy. This is actually electron deficient. Now, what it wants? It wants to attach a ring which is electron rich, because it has a preference. In case of benzene, there is no preference because only one ring. Now here two. Which one? Now simple, from if we look at this. This is electron deficient because attached to this nitro. How you can understand this bit better? This is oxygen. This is oxygen. So it is electron deficient. So this is electron deficient. So this is electron deficient. This number 2 is electron rich, but this is an incomplete word. We should write comparatively. Comparatively electron rich. So please don't make this mistake. Don't say this is electron rich. This is not electron rich compared to biphenyl, because it is electron deficient, so definitely it will be electron deficient. Okay. So comparative electron rich compared to ring number 1. Second point, nomenclature. So this ring is substituted. So we will say this is 1, 2, 3, 4. Similarly, this is 1 prime, 2 prime, 3 prime, 4 prime. So this is, what should be this name? This should be 4, 4 prime dinitro biphenyl. Okay, so keep it in mind. This is a di substitution. So this, an interesting thing is that this is a nitro, so you can reduce to prepare amine, those things, very possible. We are not into details. Similarly, if you look at this methyl, which is having a weaker plus I effect, so where the reaction will happen. So generally, based on this concept, electron rich and deficient, we can say that this is electron rich. So aromatic electrophilic substitution will happen this, but not. Why? Actually, the product is this is methyl, this I also draw bad way, but I always suggest you, please make a good practice such that your drawing is better, because this bad, worse and worst, sometimes it is difficult to understand. Students do this mistake also. They are writing right thing, but because of bad writing, it is difficult to understand what they want to say. This. Similarly, instead of that CH3, like this nitro, if it is taken about this, just what you have told, COCH3, and do the same thing, what it will result means AlCl3 and Ac2O, acetic anhydride and aluminum chloride, field capped acylation. So what will be the product? So then the product would have been this. Okay, so keep it in mind. Just this example I should also mention. Fine. Now see, why I have given this? In case of electron withdrawing group, para position, which is understandable, acceptable, because we know that this is electron withdrawing deficient. That's why this is like same explanation. But here, why this? Question, this is the product. Question, why this? Because what we have expected, our expectation is that aromatic electrophilic substitution where will happen? This ortho and para. Generally we expect, because it's electron rich. So we have expected C this, but this doesn't happen. Question why? Because this is more stable. Another thing, you have to go through that canonical form thing. If it happens at this position, for example this, then the positive, if it happens at this position instead of this, so the positive charge will come here, here, here. If you can't understand, please go back to the first part and come here. Okay, so this, after that, when it is here, then it will participate. So plus charge will come here, here, here. And now focus. That methyl group is also capable to donate here compared to that. So that is the reason. I think you may little confuse that why. If its substitution happens on this position also, then also possible. But in this case, it is experimentally observed that this substitution is more facile. Okay, compared to this. And second point, if you carry out this aromatic electrophilic substitution, there is a little bulk effect also. But when we think about simple toluene, why we did not consider this factor? Because we didn't have any option. We didn't have any choice. Here we have choice. This is 1, this is 2. Where it will go? So it will think that where I go and get better stabilization, it has an option. That's why, and in this way it gets best, because there is stable, also it is stable. But here little less crowded this thing, here more. So that is the thing. It's a, I know it's not a this excellent explanation to feel, but sometimes we have to accept in case of organic chemistry, because this is the experimental fact, and we have to explain this fact based on our previously known methodology or understanding. Okay, fine. So we have understood why this is happening. So here product will be this thing. Now, a last part of this discussion, that is, if we take OH or ONE, what will be the product? So, before going to details, I want to remind you that previously what we have studied, that if you take phenol, OH, and inorganic solvent like this chloroform and bromine, so we have obtained mono substitution. Keep this information in mind, it is important. Okay, so ortho or para, this or this, ortho or para is a mixture. Okay, fine. So generally, mainly para is the main product generally. So fine. So this mixture of ortho para. But if you, instead of CCl3, if you have taken water and bromine, what is the product? Tri-substitution. And this is an ambiguous property of this phenol versus simple double bond, because this taste is not Biak taste, I am not saying, but similar like that. So such type of thing. So this. So since we have taken this chloroform and bromine, this mono substitution is the product. And simply biphenyls are nothing. Biphenyls are nothing but actually attachment of two phenyls. Now we can say that this is a para position. This is a para position blocked with this ring. You may think biphenyl in this way. Fine. So here what is the electrophile? Here this Br plus is the electrophile. Okay, but it is not generated generally in presence of bromine molecule, so they can polarize very easily. So here generally for bromination bromine plus is, but here this is not, because this is a delta plus, this is a delta minus. So this delta plus bromine is the electrophilic center. Okay, fine. So what happens? Now there is a two chance that it can push and react with ortho versus para. But para is blocked, so no chance. It will follow this ortho attack. So this, and it will open. So the product is this is plus and this is the HBr, and ultimately what it will result? Then this charge will come here. Sorry, this is the plus charge here, then plus charge here, plus charge here, here. So in this way, actually as I told, through orthopara attack, this adjacent phenyl can participate in resonance or stabilization of the positive charge. So here ortho attack. So, and actually what is the product? The product is the ortho attack. Okay, so the product is this. Question 1. See, in this case, actually comparison comes this methyl versus this phenol. Okay, so question is fine. It is weakly donating, weakly activating. So this is, means this methyl is weakly activating, but OH strongly activating. Understood? That's why. Now it is weakly activating, that's why there is a chance of competition, but this is strongly activating, so this is rich. So this is electron rich. So aromatic electrophilic substitution, which is an electrophile, electron deficient species addition, will happen on this ring. So that is the basic difference. Question is one. Now one interesting point. As you can see, I have written that is OMe. So let's focus on this OMe example. So means what do I mean? That this OH should be substituted by OMe. Now it is still orthopara donating as well as electron rich. And what happens? So both chances and possible. What do I mean? That one is this ring substitution, another is ortho substitution. So let's draw every place. So let's draw the other ring substitution. These versus, and in this case I suggest you student, please write the double bond. It helps to understand, not that circle benzene. Okay, what we have, I have just some time before this circle thing. It is better to write in this way. It is easy to understand. Plus another chance is there. So that is the ortho substitution. This is when, is it visible? Yes, it is visible. Now question. The condition is CHCl3 and Br. Okay, Br. So question, what is the product? Actually here the both of the reagents are the product. This is ortho substitution about 60% and this is 30%. Sorry, I made mistake. This is 60% and this is 30%. So what is the conclusion of this story? Conclusion of this story is that, what is the difference? This is OH, it can undergo deprotonation easily and hold the negative charge very easily, because positive charge it can release via proton, but it is not possible in this case. Let's clean it. This is not possible in this case. So this is strongly plus R effect. Fine. So both chances possible, because if I draw the canonical form of this biphenyl, let's draw about this. So what can happen? It can push, it can push, it can push, it can push it. So in this way, what is the possible? That how this attack is happening, I want to give you an idea. That's why I am drawing this canonical form. But always keep one thing in mind: charge separation is not a very positive solution of resonance, getting more stabilization when the parent molecule is neutral one. Okay, fine. Then it attacks to the electrophile, that is Br, because it is delta plus, delta minus. Okay, so in this way this is happening, and what does it proves? That there is a chance for both, but if we provide proper condition and compromised condition, possible. See, this is OM is still, let's say, very electron rich. That's why you can think that this ortho substitution, this part is the major product, that is 60% conversion, but here in case of this other ring is less, but this happens. Okay, this. And okay, another one thing I forget to explain here, because in the first example, this example, ice water, why this is, and you can learn little more interesting thing from it. Generally, this biphenyl system, if you look at the solubility of biphenyl, they are not generally that much soluble, and generally biphenyl is solid. Okay, so this biphenyl is solid at room, generally, not nitro, the parent one is solid at room temperature. So if you provide ice water, see, this is a two aromatic ring attached to each other, so not that much having a part to solubilize this, not polar group, so that's why it is not soluble. And we have done this reaction in mixed acid, means concentrated acids are nitric acid, sulfuric acid, and nitro derivative also is not that much soluble. That's why when we add slight amount of ice water, there is clear phase separation. Means that this mixed acid, we know that sulfuric acid is a very good solvent for organic material. It is soluble. So when sulfuric acid got water, it has a more solubility in water compared to this organic medium. So it will come. So there is no one who can solubilize the product. Consequently, in ice water, these two dinitro derivative in terms of water will be precipitated. Okay, so this is an interesting chemistry, because from what we have learned from this chemistry, if we have a very big aromatic ring containing molecule, it is easier to separate them after reaction. How? by putting water into the reaction medium, because it has a less solubility, so it will instantly precipitate. Okay, so this is the understanding. So this is the end of this discussion. What we have learned today? We have learned today about the aromatic electrophilic substitution on biphenyl. I believe it's a difficult and interesting point because conjugated. And why biphenyl gives substitution on other ring? First, with resonance stabilization of canonical form. Second, when it will give the ortho substitution of the same ring, this, and why when it will give other substitution means 4 prime. Okay, so this we have learned today, lots of chemistry. So I believe this may be helpful for you. So if it is really helpful for you, I suggest you please help my channel to grow. First of all, please subscribe my channel Chemistry the Mystery of Molecule, and please press the bell icon to get the notification of every single video I upload. Second, share this video among your friends such that many people could be benefited from my effort, and this is a very it's a satisfaction for us, satisfaction for me that what I have done for you, it's helpful for you, people are getting benefit. And another last part of this thing is that please like this video and make some good comments, because this is the biggest achievement in the field. It gives a very good satisfaction. So thank you everyone again. See you in my next video. Till now, stay happy, stay blessed.